There we go.
Great. Thanks, Miguel. So I'm going to start out today by talking a little bit, focusing primarily on the completeness hypothesis. And I'm going to set up just a little bit of the technology that will be useful for understanding this, as well as these Chern-Weil global symmetries, which is a term which Jake will define and then discuss in more detail. And all of this is going to be based on a little bit on a paper that's already out with of mine with Shuheng Xiao, as well as a couple of papers at least, which are to appear with Jake, myself, and then Ben Heidenreich, Miguel Montero, Matt Reese, and Irene Valenzuela. So a quick outline. As I say, I'm going to introduce higher form global symmetries, talk about completeness, and then Jake will take over and talk about Chern-Weil global symmetries and end with some conclusions. So first of all, higher form global symmetries are a concept which have really taken the quantum field theory world by storm since this seminal work of Gallardo, Kapustin, Seiberg, and Willett in 2014. The idea behind these symmetries is that they generalize the notion of an ordinary global symmetry to the case where the charged operators are supported on Q-dimensional manifolds. So the case of a zero form symmetry with Q equals 0 corresponds to the ordinary global symmetries that we know and love, where the charged operators are local operators associated with points in space-time. Global symmetry transformations form a group which may be either discrete or continuous. For an ordinary global symmetry, it may be non-abelian or abelian, but for a higher form global symmetry, the symmetry group is necessarily abelian. And if G is continuous, then usually under reasonable circumstances, there will be a conserved D minus Q minus 1 form, another current, which is closed. So the statement that this current is closed, or sorry, that the current is conserved is equivalent to the statement that this D minus Q minus 1 form is closed, D of J equals 0. Symmetries are implemented by symmetry generators, also known as charge operators, which are labeled by elements of the group G and associated with manifolds of dimension D minus Q minus 1. These operators satisfy a fusion law. So if I take one operator labeled by G and another operator labeled by G prime associated with the same manifold M, I can fuse these things together to get a third operator labeled by this operator, labeled by the element G double prime, where G times G prime equals G double prime in the group multiplication. So the fusion law is equal to the group multiplication law. These operators are topological. And this is really a hallmark of a global symmetry, the presence of these topological symmetry generators labeled by elements of the group, which fuse according to the group fusion law. By topological here, I mean that if I take one of these operators and I smoothly deform the manifold M on which it lives to some other manifold M prime, this will not affect any correlation functions, any physical observables involving this operator, provided that in this deformation process, I don't cross over any charged operators. For the case of a global symmetry, which is something that Jake and I will primarily be focused on today, you can be a little bit more explicit about the form of these operators. They're given simply by the exponentiated integral of this another current, J, over the manifold M. And alpha here labels the element of the group. Symmetries are associated with word identities. And in the language of these charged operators, the word identity says that if you take one of these symmetry generators and you surround one of these charged operators, this is going to be equal to the charged operator you started with times some phase in the case of a U1 symmetry or an abelian symmetry, and more generally, some representation of the group G for the non-abelian symmetry. And this depends on both the charge of the operator V as well as the element of the group G. Pictorially, what's happening here, the word identity says that if I take some charged operator, I surround it by one of these symmetry generators. Because this symmetry generator is topological, I can shrink it. And so I can shrink it and make it smaller and smaller and smaller without affecting the correlation function. And if I shrink it all the way to a point, the word identity says that I'm going to get back this charged operator I started with times this phase. So a simple example, we can consider U1 gauge theory. So just ordinary Maxwell term. There's no electrically charged particles. There's no magnetic monopoles. In this theory, there will then be two U1 one-form global symmetries, an electric one and a magnetic one. And the associated other currents in 4 dimensions are two forms. The electric current given by star F up to these normalization factors, and then the magnetic current given by F. And the statement that these currents are conserved follows simply from Maxwell's equations. In the absence of any electrically charged particles, d star F equals 0. In the absence of any magnetic monopoles, dF equals 0. These are one-form symmetries in 4 dimensions, which means that the charged operators live on one-dimensional manifolds, and they're nothing but the Wilson lines and the 't Hooft lines of the theory, respectively. So the word identity, focusing, for instance, on the electric one-form global symmetry, tells us that if I take some Wilson line, which lives on some one-dimensional manifold gamma, I can surround it by a two-sphere, which supports one of these symmetry generators, the integral of the another current over this two-sphere. And this will act on this Wilson line by giving me back the Wilson line I started with times this phase. And you see that this phase is charge Q of the Wilson line, as well as this element alpha of the group. Now, we in quantum gravity theories, we expect that generically we will not have, we expect that we will never have global symmetries, which means that in a consistent theory of quantum gravity, these global symmetries need to either be broken or gauged somehow. And I'll say a little bit more about this momentarily. But that means that understanding how these symmetries are broken is going to be an important aspect in understanding how effective field theories are completed into consistent theories of quantum gravity. So one way to break this global symmetry is to add in some charged particle. So looking at focusing now on the electric one-form symmetry, we have this current star F, and suppose that we add to the theory some particle, for sake of argument, we'll say it's a fermion, of charge n. So you can see immediately from the equations of motion that this is going to break this one-form global symmetry, because star F is no longer conserved in the presence of this fermion field, and so the symmetry is broken. In the terms of these charged operators and charge operators, the way to understand this is to note that in the presence of this charge n matter, the charge n Wilson line can end. So it can end at some local excitation of the fermion field, and as a result, this topological symmetry generator can be smoothly unlinked from this Wilson line. And this allows us to consider the following sort of thought experiment. Consider this correlation function here. We have some topological symmetry generator which surrounds a Wilson line of charge n. And we assume the Wilson line can end on the fermion. Now we can compute this correlation function in two different ways. First of all, we can use the word identity to shrink this symmetry generator, and that's going to give us the Wilson line we started with times this phase. But on the other hand, we can also unlink the Wilson line from the symmetry generator. Now we can shrink it to 0 size, and now we'll just pick up a trivial phase. So what this is telling us, equating the left and right hand side, is that e to the I alpha n must equal 1, assuming that this operator is a topological symmetry generator. And therefore, we learn that in fact, e to the I alpha must be an nth root of unity. So in the presence of this charge and matter, it's no longer the case that all of the symmetry generators are topological. The only ones that are topological are nth roots of unity. And therefore, the one-form global symmetry has been broken from U1 down to a Zn subgroup. So this, as I say, is important because in quantum gravity, we expect that there will not be any higher form global symmetries. This was argued for the case of an ordinary global symmetry by Hawking in the 80s, and there's a sort of this famous summary of this argument in Banks and Seiberg. More recently, Harlow and Oguri have given this argument in the context of ADS-CFT, which extends to the case of these higher form global symmetries, provided that P is less than du minus 2. So this is sort of the statement that we, the well-supported swampland statement that we tend to believe. Now, what I want to do, first of all, is tie this to a different swampland statement, which is the completeness hypothesis. The completeness hypothesis, due to Polchinski, says that in d-dimensional gauge theory coupled to quantum gravity, you must have states in every representation of the gauge group. So by states here, I mean you could have particles, you could have multi-particle states, but somehow every representation should be included in the spectrum. And it's often noted that this is actually related to the absence of global symmetries. And this is actually a statement that can be made even within the context of quantum field theory. So we can, although this statement here deals with quantum gravity, the relationship between the completeness hypothesis and the absence of higher form global symmetries is a relation which exists even within the context of the quantum field theory. And at least in certain cases, it's easy to see why this conjecture exists and why this relationship exists. So let's consider the U1 gauge theory we just saw. We saw that if there were no electrically charged particles whatsoever, we had this U1 electric one-form global symmetry. We just saw that when we had particles of charge n, this U1 symmetry is broken down to a Zn subgroup. If we have states of every charge, that means that this U1 is going to be completely broken, and there's no electric one-form global symmetry whatsoever. So in this case, you can see this one-to-one relationship, where if we have states of every charge, there's no electric one-form global symmetry. And if we do not have states of every charge, then there is some electric one-form global symmetry. So there's this one-to-one relationship between the presence of these electric one-form global symmetries and the completeness hypothesis. But this, however, is not, this relationship does not hold in general.
Tom, can I ask a question just from the previous slide? This logic, does that say that every charge has to be present? Or like if I have like, you know, charge 1, 2, 3, 4, no charge 5 object, and then 6, 7, 8, 9, what kind of symmetry would I get? If there's no commutants of the different charges of the ZNs, then you would get nothing. You break everything, no?
Yeah, so the key here is that multi-particle states will work too. So you can construct a multi-particle state of charge 5 in that example. And the way to understand why that's fine is because if I go back to this argument, you know, if I have a charge, if I have 5 charge 1 Wilson lines that end on charge 1 particles, I can fuse them all together to get some charge 5 Wilson line, which is going to end on some multi-particle state, essentially.
The statement is just there shouldn't be some kind of empty sublattice or something like this.
Or the statement is that Hilbert space must contain every representation.
That's right.
Yeah. Okay, thanks.
Thanks. So as I say, there's actually a counterexample to this statement. So Harlow and Oguri pointed out such an example in their paper. So you can consider S3 gauge theory. And what you'll find is that even if you're considering pure S3 gauge theory, so there's no matter in any representation, you will still not have any one-form global symmetry. So this is sort of a naive counterexample to this relationship between global symmetries and the completeness hypothesis. But there's actually a more general story which takes place here. It may be true that there's no one-form global symmetry, but there are more general topological codimension 2 operators. What do I mean by this? Well, you remember a one-form global symmetry is associated with codimension 2 topological operators, which fuse according to the group multiplication law. For these more general topologies of codimension 2, the fusion law will be more complicated. So rather than fusing 2 of these guys to get just a third operator, you can fuse 2 of them and get a sum over topological operators. And one can show that the completeness of S3 gauge theory is actually equivalent to the absence of these more general topological codimension 2 operators. So this is one example where we have a finite non-abelian gauge group Another example of this phenomenon occurs in perhaps a somewhat simpler theory to understand.
Excuse me. So is general statement known to that effect?
Yes, and I'll get to it in a few slides.
Okay.
So another example is O2 gauge theory. So O2 can be thought of, can be written as a semi-direct product of Z2 and U1. And so one way to think of O2 gauge theory is that you start with U1 gauge theory, just ordinary electromagnetism. And then what you do is you gauge charge conjugation. So the Wilson lines of this theory are going to be labeled by representations of O2. And the representations of O2 are given by the trivial representation, the determinant representation, which takes an element of O2 and gives you back either plus or minus 1, as well as being, and there's a family of representations labeled by positive integers of Q. And a Wilson line in one of these representations can sort of be thought of as the sum of the U1 Wilson lines of charge Q and minus Q before we gauge this Z2. The topological codimension 2 surfaces in this theory are going to be labeled by some angle theta between 0 and pi. So the theta equals 0 is just the trivial surface. Theta equals pi is essentially the same as the theta equals pi surface for the U1 gauge theory. And this thing is going to generate a Z2 one-form global symmetry. But then for any angle between 0 and pi, the surface in the O2 gauge theory, labeled by theta, can be thought of as the sum of the U1 surfaces, labeled by theta and minus theta. And these particular surfaces are not going to generate a global symmetry because they're not invertible. There's no way to multiply two surfaces of this form together and get back the identity surface. So whereas this thing is invertible, it squares to the identity, these guys are not invertible, and therefore they do not generate any one-form global symmetry. And so we can understand what's going to happen to each of these, to the topological surfaces when we have matter in different representations. So here, for O2, the adjoint representation is the determinant representation. So, so this thing, you sort of have a gluon in this representation. You can add in matter in other representations, and you can see how this affects the spectrum of topological operators. So if you add in some matter in the charge 1 representation, this is going to give you a complete spectrum by considering the tensor products and considering multiparticle states. And indeed, there will be no topological surfaces whatsoever. So when the spectrum is complete, there are no topological surfaces. When n equals 2, if you just add in matter in the charge 2 representation, you'll get states in charge 2, 4, 6, 8, and so on. And this is going to break a number of the topological surfaces and render them non-topological. But you'll still have this theta equals pi surface. And so you'll still have a Z2 global symmetry. So the spectrum is incomplete, but there's still a one-form global symmetry. In the case of n equals 3, this Z2 is broken. So there's no more one-form global symmetry, like in the S3 case. However, the spectrum is incomplete, and there is this more general topological surface. So this is an example of a topological surface which is not invertible. It does not generate a global symmetry, and yet it remains topological even in the presence of charge 3 matter. So more generally, the statement is that there will be these topological surfaces if and only if the spectrum is incomplete. And so this is pointing us to a more general statement, which Hiroshi was asking for. So the usual relationship between completeness and the absence of these electric one-form global symmetries that we saw in the U1 case, this is generally true whenever G is a compact connected Lie group. So, you know, U1, SUN, SU3 times SU2 times U1 mod Z6, most of the examples that we're familiar with in particle physics. Or if G is a finite abelian group. So Zn or Zn times Zn, or even a product of groups of this form. However, for a more general disconnected Lie group, like O2, for instance, or On more generally, or for a finite non-abelian group, this statement needs to be revised somewhat, and the correct statement is that the completeness hypothesis is equivalent to the absence of these more general topological codimension to electric surfaces. So what we've done here then is we've sort of revised this standard lore, which holds that the spectrum should be complete if and only if there's no electric one-form global symmetry, and we've replaced it with this more general statement.
Do you know?
Yeah.
Do you know when topological operator makes symmetry? Is the invertibility sufficient?
It is, yes.
Okay.
So this actually brings up a more general, this sort of raises a more general statement, a natural revision of another bit of standard lore. So we believe, as we saw, that there are no p-form global symmetries in quantum gravity. And what we see now is that these p-form global symmetries are actually just special cases of these more general topological operators. And so it's very natural to conjecture that in a d-dimensional theory of quantum gravity, there should not exist these more general topological operators of codimension p+1 for the same dimensionality. Now, what's interesting is that actually the argument of Harlow and Oguri does not carry over very naturally to this particular case. So the argument they have given would need to be modified in order to exclude these more general topological operators. Nonetheless, this is a very natural conjecture to make based on our understanding of quantum gravity, and so it would be interesting to try to understand it further. So so this concludes my part of the talk, and now what I want to do is switch over to Jake and let him tell you about sort of a different direction of no global symmetries in quantum gravity. Thanks.
Sorry, Tom?
Yeah.
Hi, before you sign off, just a question about that. How much of what you just said depends on the space-time manifold being compact? Like in a non-compact case, wouldn't you have to modify this for boundary conditions near infinity?
So you're asking about the space-time of the quantum gravity space-time.
Yeah. Are you sort of assuming a Euclidean compact space-time, or can you extend it to asymptotically locally flat or some other more general?
Sorry, are you asking about this last statement about the absence of topological operators, or are you asking about the relationship between completeness and?
I think the entire analysis around higher form symmetry is somehow natural when the spacetime is compact, and it would appear that it should have depended on choices of boundary conditions otherwise, which would make me think that if you were studying quantum gravity in a particular class of spacetimes, the statements could be different.
Yeah, I see what you're saying. See, I haven't thought too much about it. The Harlow and Oguri argument took place within the context of ADS-CFT, right? So there you have actually this boundary of space-time, and there. So what they did was sort of a more sophisticated analysis, and a large part of what they had to do was sort of understand the dictionary between these operators in the book, and the operators and the boundary. So I think that probably some sort of analysis should apply there. But I do agree that there are subtleties when these topological operators have boundaries that need to be taken into account, and I haven't thought too much about it yet.
I see. And one question, Tom, related to your last comment about the relation between baby universe hypothesis and topological operator. It's a consequence of the baby universe hypothesis also that there are no topological operators. So it kind of unifies that picture to a very simple statement. Because in fact, more precisely, there is a topological operator, namely the identity operator. And that's a statement that the baby universe Hilbert space is one-dimensional. So any other operator would have by correspondence be a non-trivial baby universe Hilbert space, and that's against the baby universe hypothesis. So that's consistent with that.
Thanks. Yes, Jake actually has pointed this out to me recently. So with that, I should turn things over to him. Thanks.
maybe before I start, just a comment on the previous question about whether this is something to do with compact versus non-compact spacetimes. As I understand it, these statements of no global symmetries and this discussions of operators is local in the bulk, at least in quantum field theory, it's local. In quantum gravity, maybe you want to say it's as local as possible in low energy effective description or whatever. And in fact, I think Daniel Harlow has a recent paper where he tries to modify the argument that he and Hiroshi gave, instead of using entanglement wedge reconstruction from ADS-CFT, instead using sort of the entanglement island picture to make the same argument. So it should probably be thought of as local as anything is in the bulk in quantum gravity. Yeah, but anyway. Okay, should I start then?
Yeah, go ahead.
Cool. Here, let me share my screen. Can you see that? Great. Okay, yeah. So as Tom said, so this collaboration has been working on a number of papers, all related to the questions of global symmetries in quantum gravity and completeness of the spectrum and these various sort of kinematic questions. And so I'm going to talk about another project that we've been working on Chern-Weil, what we're calling Chern-Based Symmetries. And so again, this is with Tom and I, and then Ben Heidenreich, Miguel Montero, Matt Reese, and Irene Valenzuela. So I will just want to sort of start by emphasizing that there's this current trend in the Swampland program, which is to realize that the statement of no global symmetries is actually a lot more powerful than might be naively expected. When I first heard the statement, it's sort of no global symmetries, okay, whatever. But what we're finding out is that actually coming up with a quantum system that has no global symmetries at all is actually very difficult and is very constraining on the dynamics of the theory. So we're going to provide in this paper another example of that trend regarding what we're calling Chern-Weil symmetries of gauge theories. So these are higher form symmetries. They're I didn't note it here, but they're U1 higher form symmetries, and they're present in any quantum field theory or quantum gravity that has a gauge theory in the low energy description. And these are symmetries defined by currents, which are given by traces of wedge products of the gauge field strength. So in the case k equals 1, this might just be the magnetic symmetry, say, of a U1 gauge theory, and for higher k, it might be instanton number or higher generalizations of that. The conservation of these currents follows from the Bianchi identity. So if you hit J with the exterior derivative, you can move it inside the trace and it becomes a covariant derivative, and then hitting F is 0 by the Bianchi identity. Put differently, these currents define topological invariants of the gauge bundle. So these are things like Chern classes or Pontryagin classes or other characteristic classes. And as a result, these symmetries are pretty hard to break. You can't break these symmetries by turning on any terms in the Lagrangian because they're properties of the field configuration, they're topological properties. And so in order to break them, you'd have to allow more general things than smooth, more singular configurations than smooth gauge fields. And so they're not impossible to break, but they're a little harder to break than other symmetries, at least from a low energy perspective. And of course, in broad strokes, these are symmetries. And so they need to be broken or gauged in quantum gravity like any symmetry. And again, that statement by itself is not necessarily so interesting. But what we're going to see is that the details of how these symmetries become broken or gauged is actually going to reproduce a number of features that we're very familiar with from string theory. In particular, we'll see that the breaking and gauging of these symmetries tells us a lot about axion physics, as well as branes dissolving in other branes. And these are both phenomena that we're very familiar with in string theory. Usually those phenomena, string theory is this very powerful machinery, and we can compute things explicitly from the bottom up. And what I'm going to explain in this talk is how we can reproduce some of those features just by considerations of global symmetries and their absence in quantum gravity. Okay. So I'm mostly going to focus on the case k equals 2 here for this talk, just for simplicity. And so this is the case of instanton number. So if we have G gauge theory in D dimensions, we have a global D-5 form, U1 symmetry, with current given by trace F wedge F. And this measures instanton number And this is, of course, well known in the case of d equals 5 or 6, for example, in the case of, say, SCFTs, right? In d equals 5, this is an ordinary symmetry, and it's the symmetry that counts instanton particles. And d equals 6, it's a one-form symmetry, and it counts instanton strings. So what would it mean to gauge this symmetry? Well, that's pretty straightforward. We would just take some d-4 form gauge field, C d-4, and add a coupling in the Lagrangian between our gauge field and trace f wedge f. So this is a sort of triple Chern-Simons term that we're very familiar with. And just to point out, in d equals 4, this is an axion. And this is very familiar, of course, from string constructions. But the point is that this gives a new perspective on the necessity of axions in string constructions. The point is that the axion is there in order to gauge a Chern-Weil global symmetry. And in this case, it's a -1 form global symmetry. So maybe I should say a couple words about what I mean by -1 form symmetry. So what is a -1 form symmetry? Well, if we just take our normal formulas for what a symmetry is and we extend them to the case of p equals -1, well, we have a top form current. So this is like the Chern-Weil current in d equals 4, instanton number in d equals 4. And the charge under this, oh, sorry, it should be charge, not charged, is defined by an integral of the current over space-time. So for example, instanton number. So this is a charge associated with space-time manifold, not a spatial slice or a lower codimensional submanifold. And I want to point out that the conservation of this current is actually trivial because it's a top form. And so d of it would be a 5 form in 4 dimensions. And so it's trivially conserved. This is part of why the notion of -1 form symmetry is a little bit less well defined than other symmetries, but it still seems like there's some sense in which it's a meaningful thing to discuss. What would it mean to turn on a background gauge field for this symmetry? Well, that would just be turning on a parameter such as a theta angle. That means we're taking our dynamical fields and coupling them to a background fixed parameter such as theta. Gauging the symmetry would be promoting theta, our background gauge field, to a dynamical gauge field, making it a dynamical axion. And this is related to the Swampin conjecture of no free parameters or the baby universe hypothesis. So gauging at least is very clear what it's meant to gauge a -1 form symmetry. Breaking a -1 form symmetry is less clear because, as I said, the conservation of this current follows from the fact that it's the top form. And the approach that I'm going to take in this talk and that we mostly take in our paper is an approach of I know it when I see it. So I think the question of what is the proper notion of -1 form symmetry is a really interesting and deep question, but it's not the main thrust of our paper. So we're mostly going to work in examples and not try to give a general definition, although I think it's a very interesting thing and something that at some point should be figured out what the right definition is. And if this makes you less comfortable, we can also just always assume that we're talking about gauge fields propagating in more than 4 dimensions, and then say that, well, we then compactify to 4 dimensions. So that's one way to put all of this discussion on completely rigorous grounds. But I should say, I do think that there's a sense in which -1 form symmetries make sense, at least in quantum gravity. OK, so does anyone have any questions about what I've said so far?
Sorry, quick question. So if you gauge this, theta is a periodic parameter, so it has pi1, and that generates some 2-form symmetry, right? You also want to break that. How would you do that?
So that would require having strings charged under the dual B field, say in 4 dimensions. And so that B field will participate. It will transform. That B field will have a Green-Schwarz transformation under gauge transformations of our ordinary gauge field. And so we'll need to add strings that have on their world volume certain degrees of freedom, such as, for example, as you're familiar with in the heterotic string. I'm not going to get into a ton of detail in this, but that whole question of what happens with all global symmetries in this example of a theory, we're going to address in at least one of these papers and potentially talk about it, some aspects of it in both. But it's a very good question. Yeah.
I see. Thanks.
Yeah. There's a lot of interesting things to say there, but maybe save for another discussion. OK, cool. Any other questions? So in order for this argument to work, for me to be able to argue that the presence of this symmetry means there should be an axion, we need to avoid the other possibility, right? Any symmetry in quantum gravity is either broken or gauged. It's not just straight up gauged. And so we need to talk about what happens if the symmetry is broken. So the first way I want to describe breaking a Chern-Based symmetry, again, to put this on rigorous grounds, we could work in more than 4 dimensions. So one way to break them is by unification. So suppose that we Higgs a gauge group down to a product of groups, such as, for example, just completely pulled out of a hat, breaking SU5 down to SU3 cross SU2 cross U1, maybe mod Z6, I should say. In the UV, we have a single Chern-Weil current corresponding to instanton number for the SU5 gauge field. But in the IR, we have 3 Chern-Weil currents, one for each factor. So we have one for SU3 instanton number, SU2 instanton number, and U1 instanton number. And in the IR, these are all separately conserved. But in the UV, only one combination is preserved. It's the combination that corresponds to JSU5. And so what's happening? Well, what's happening is that the other linear combinations, such as each individual instanton number, are broken at the UV scale. And one way to think about this, right, what it means to break a symmetry is to say that charge for the symmetry is not conserved. So here what I'm saying is that if you take an instanton for SU3, you can imagine shrinking that instanton below the Higgs scale and then rotating it within the UV gauge group. So it points, say, in the direction of SU2 instead of the direction of SU3. And what you find is that these instanton numbers for the different factors are not separately conserved. Yet there still is one conserved combination corresponding to the UV gauge group SU5. So the pattern is that we have multiple Chern-Weil currents for non-abelian gauge fields in the IR, and only one combination is being preserved in the UV. We can see a very similar pattern outside of EFT. So we can also break Chern-Weil symmetries in the small instanton limit, as is very familiar in string theory. So for example, in heterotic string theory, we have a Chern-Weil current corresponding to the E8 cross E8 or spin 32 mod Z2 gauge field. And as is well understood, when we take the small instanton limit of this charge, the current is broken because gauge theory instantons can turn into heterotic 5 branes and then go off and do their own thing as a separate excitation. This is to say that the two charges, instanton number for the heterotic gauge field and 5 brane number, are not separately conserved, but only a linear combination of them, as well as a charge corresponding to the Pontryagin class of the tangent bundle. So only one linear combination is conserved, and this is the combination that's gauged by coupling to B6, which is the electromagnetic dual of the string theory 2 form, B2. So again, we're seeing that we have that the Chern-Weil current charge alone is broken, but a combination of it with some other charge is gauged. Another example of this is small instantons on stacks of dp branes, right? So stacks of dp branes have a non-abelian gauge theory on their world volume, and you can shrink those instantons and detach them as independent objects, dp minus 4 branes. And so again, there's one linear combination that's conserved. It's a linear combination of the Chern-Weil current on the brane world volume, as well as dp minus 4 brane number, and that's the combination that's gauged by the R gauge field, cp minus 3. Okay. So in fact, in every non-abelian example we know, so every example of a non-abelian gauge theory, in quantum field theory and quantum gravity, the only way we know how to break the Chern-Weil current leaves a combination of the Chern-Weil current itself and some other currents conserved. Now, we can't prove that this has to happen, but this is the pattern we're seeing in every example we know. And I should emphasize this is for non-abelian gauge fields. And indeed, if this pattern persists, then no global symmetries in quantum gravity would tell us that the conserved combination must be gauged in the following way. And again, in d equals 4, that tells us that there should be a dynamical axion coupling to the Chern-Weil current of any non-abelian gauge theory, in particular to the QCD instanton. And of course, that's phenomenologically interesting because it might help us address the strong CP problem. Right, one way to address.
May I ask a question?
Yes.
So I just wanted to make sure I understand what a non-trivial statement is.
Yes.
So are you requiring that there has to always be some combination that is conserved, namely that of course, symmetry has to be either broken or gauged. And it could be that all symmetries are broken completely, in which case there is no current to be gauged. Are you saying that that will not happen?
So I'm not saying that I can show that that can't happen. What I'm saying is that in every example we know.
You are claiming as a conjecture that there ought to be at least some combination, some non-trivial combination that is conserved, which and then has to be gauged.
I don't know if I want to say it quite that strongly.
But if you don't want to say it, what's the statement?
Well, that is the statement. I just don't know that I want to state it quite so strongly as a conjecture. I don't know.
So it is a statement. You are claiming
it is a statement that we're observing this pattern.
Current that has to be gauged.
For non-abelian gauge theories, in every example we know of how to break this symmetry, so there's still a conserved combination. Yeah.
Thank you.
I don't know. Do any of the other authors want to comment on that?
Well, I think that Jake is coming from a more mathematical background where he doesn't like to use conjecture. So the rest of us physicists can.
You can call it as a hypothesis.
We'll go ahead and conjecture this, and Jake will go ahead and maybe speculate or hypothesize.
Fair enough. Yeah. Yeah. No, I think that this is probably true. Yeah. The only concern is that we're not being smart enough, and we haven't considered some other physics that might happen. In every example we know.
And your hypothesis apply only to Chern-Weil symmetry?
So this is specifically with regards to the instanton number symmetry of a non-abelian gauge field. The reason we introduced this terminology of Chern-Weil currents is because we consider more general ones than just.
So hypothesis is that there ought to be always at least one conserved combination that is gauged.
For non-abelian gauge fields, yes. Yeah.
And is this related to some other principle that you can associate or not?
This fact?
The existence of this, in other words, is this a standalone conjecture or statement or whatever, or this is connected?
I haven't thought about it in these terms.
So nothing goes bad if there's no such current, in other words.
No. I mean, you could easily imagine a situation where it's just directly broken by some effect. Like you could maybe let me put it this way. I don't see anything wrong naively with just putting in some effect in the UV, which just explicitly breaks this current. It's just that no effect we know of does that job, which is why I from the perspective of no global symmetries, there would be nothing wrong with just breaking everything. Yeah.
Maybe I could make one more small comment here, which is that, what we're noting here is this phenomenon, which seems to be true in all the examples that we know of, and we're not saying that there couldn't be another thing, but I think what Jake is really trying to point out here, right, is that there are these two phenomena that we see in string theory. One is that in all the examples we know of, there's this combination that's conserved, one that there's always at least one combination which is conserved. Another phenomenon we observe in string theory is that axions are ubiquitous. And a priori, you might have said that these two phenomena are just totally unrelated. But what we're seeing here, what Jake is explaining, is how these two phenomena actually unified by this Chern-Weil perspective.
Sorry, may I ask a stupid question? What about below the axion mass scale? So the axion will get a mass from instantons, and if I'm in the infrared, I don't see that axion. So what's the situation then?
That's a very good question. I'm going to say something about that on the next slide, but one thing to say now is that it's perfectly fine in quantum gravity to have approximate symmetries in the infrared. So for example, as the symmetries Tom was discussing in the previous part, imagine you have a U1 gauge theory where all the charged states are massive. So above the mass of the lightest charged state, you have an approximate one-form global symmetry. Now, the question of at what mass does the effect that breaks the symmetry have to come in is a question of how close to an exact global symmetry can you have? And I think Tom and some collaborators have been thinking about this question. And one thing to say is that it should be badly broken at the Planck scale, but that doesn't mean that you have to have an infinitely light axion.
Sorry, but I'm confused. let me have matter such that the non-abelian gauge group survives in the infrared.
Yes.
Wouldn't it be a contradiction? I mean, if the infrared, so I think this theorem should be, or conjecture should be such that they are absolute, and in the infrared they're simply true. So you have the non-abelian gauge symmetry, so you have the F wedge F, and you must see the axion. If you don't see it, your conjecture is wrong. Isn't that naive?
No, I mean, part of the issue is that I think you're assuming that the statement no global symmetries applies in the deep infrared, and it doesn't. Right, it only applies. The question of exactly at what scale it applies, strictly speaking, it only applies to the exact theory, right? The exact theory in the UV. But there's definitely a sense in which you can strengthen that and say that the symmetry should be broken before you get to the Planck scale. And that's the question of how close can you have an approximate symmetry.
Maybe so mentioning the analogous thing in the case of just the F and star F currents that Tom mentioned earlier in a U1 theory, right? So in the real world, magnetic monopoles might exist, but they're very heavy, and the electron exists and it has a mass. And you could say the same thing. If we look at the photon at low energies, we have global symmetries. But the point is they're not exact global symmetries. They are broken by the existence of these charged objects. I mean, I'm presuming the magnetic one is broken by the existence of something that we haven't found yet. And so we just know that low energy theory is like, I mean, it's consistent in quantum gravity because it happens in our universe, that we can have very good approximate symmetries at low energies. And so the question is really about the breaking in the UV.
Oh, I see. So you're saying the axion, the presence of the heavy axion leads to a breaking of that global symmetry. Is that a statement?
Gauging.
Well, a gauging of a linear combination of that.
At low energy is not gauged. It then must be broken. I mean, you just said.
I think there's a bit of a logical fallacy, which is that the statement that there's no global symmetries in quantum gravity doesn't apply in the deep IR.
No, I understand that, but so what about, so you have this FHF in 4D in the infrared because you have a non-abelian global symmetry. So it's a zero form global symmetry, right?
Say in 5.
-1 form global symmetry, sorry, right?
Yeah.
So in that case, with a non-abelian gauge group deep in the IR and no axion visible, what's the status of that -1 form global symmetry? Gauged or broken?
Just given the IR theory, it's an exact symmetry. But the question is, how does that become UV completed? And I think a very reasonable question is, what is the mass scale of the axion? So for example, is the axion mass scale set by, say, the QCD instanton, or could it be way more massive? And I'll say a little bit about that question on the next slide. Yeah. I think the question isn't, is it massive? The question is how massive.
Conjecture that it's always gauged. Isn't that the statement?
The statement is that it's always gauged in the yeah.
But it's always gauged.
It appears in a linear combination of current that's gauged.
Yeah, but there will always be an axion then. If it's some
that would be the conjecture for non-abelian gauge theories.
I think that's the answer to Arthur's question then, isn't it? Because he was saying, if you're in the IR, you don't know if it's broken or gauged because you don't see the massive particles. But you say it's always gauged.
Sure. Okay. Yes. Yeah. That's a good way to put it. Thank you. Okay. Any more questions on this slide?
I have a somewhat naive question. So in some example of cyber duality, on one side you have gauge group, on one side you have matter. Presumably -1 form symmetry now is carried by matter. And then what's wrong with adding some mass term to break this?
So that goes to the question of exactly what's the proper definition of -1 form symmetry. In some sense, every term in the Lagrangian potential term you could write down generates a -1 form symmetry because it represents a parameter you could add to your theory, right? Because you could add any D-form operator to the Lagrangian coupled to some parameter. And if we believe the statement of no free parameters in quantum gravity, then something like that should be true. And you can even talk about things like mass terms as -1 form symmetries. I don't know the strictly correct thing to say there, which is why I want to restrict to the case of these symmetries where we have a semi-classical description and know what we're talking about. Again, if it makes you happier, we could talk in 5 dimensions or more. But I think you're right. I think that things like mass terms are also examples of -1 form symmetries. Any parameter in Lagrangian, in some sense, is an example of a -1 form symmetry. Does that answer the question?
I see. Thanks.
Yeah. Yeah. Okay, great. This is a good discussion. Anything else on this slide? Okay, so let me go to the next slide, which may help address some of these questions about axions, which is one of the big issues with using axions as a solution to the strong CP problem. And I should apologize before I get into this that I am not a phenomenologist and I don't know the history of this issue. I know what my collaborators have told me. But a very common issue with axions as a solution is the axion quality problem. And what's the issue? The issue is that if you have different contributions to the axion potential, those different contributions will generically have different positions of their minima. And so if you expect to use the axion to tell us why the observed theta angle in our universe is so close to 0, from a perspective of effective field theory, that requires incredible fine tuning to get all the minima of the different contributions to align. And I just want to point out that this perspective of Chern-Based symmetries might help. And the new perspective is that the axion has a job to do. It's there in order to gauge a symmetry. And gauging a symmetry is a much more restrictive thing than just having random terms. It says that it needs to couple to the current of some symmetry. There's some structure. There's a little bit more structure. And from this perspective, other contributions to the axion potential represent other objects, so other instantons for other gauge groups, or D-brane instantons, other types of effects that are also charged under this same -1 form symmetry or higher form symmetry in higher dimensions. And so when we have multiple objects charged under the same symmetry, those objects need to be able to turn into one another. Otherwise, we have a global particle number symmetry, where we have, say, 2 objects with the same charge that can't turn into each other. And so in order to avoid new global symmetries, we need to require that any other object that contributes to the axion potential would need to be dynamically connected to the QCD instanton. So unifiable in some sense. So this is like what happens when we have a gut unification of QCD with some other gauge groups. And it's also what happens in the case of the small instanton limit breaking. So this doesn't solve the axion quality problem. I can't argue that just because this effect happens that the potentials have to have aligned minima, but it suggests a new way to think about it, which is to say that these other objects have to be related to the QCD instanton in a way besides just the fact that they couple to the axion. Okay, does that help Arthur at all, or anyone else? Does anyone have any other questions about this?
I'm not sure I understand the statement here. So
yes.
Take standard model. You have SU2, you have SU3, and so on.
Yes.
You have instant numbers. They don't have to be independent axions. Are you claiming that even if you don't have grand unification, they have to be related?
Well, if I don't have grand unification, right? If I have separate gauge groups all the way up to the UV,
yeah,
then I'd have separate currents for each different gauge group.
Right.
The claim is I would either need dynamic. I think the claim is that I would need separate axions for each gauge group.
Right. So this would, the axion quality problem will hit you there or
not? What was your question? I didn't quite hear you.
That be related to the axion quality problem you're talking about or not?
Yes. Yeah. Right. Another possibility is that some other thing that couples to our QCD axion doesn't connect and generates a separate symmetry. In that case, you would need to have another axion to gauge that other combination. But then you could just redefine your axion field by some combination to find the one that couples just to QCD. And so at the end of the day, you would still just have an axion coupling just to QCD. The point is, at the end of the day, all the symmetries need to be broken or gauged. You can't leave a combination that's not broken or gauged. Yeah, cool. All right. So this is what I have to say about non-abelian gauge fields. So let me take a second and now talk about abelian gauge fields, where the story is different. So for abelian gauge theory, non-abelian gauge theory, we saw that Chern-Based symmetries are pretty hard to just directly break. We always find this pattern where there's a combination of the current with other currents. In abelian gauge theories, that's not true. And in abelian gauge theories, we can just directly break the Chern-Weil current by adding magnetic monopoles. with the current Jm, Dirac function, delta function localized source on the world volume. And we can compute, in this case, that dj is going to be 2 times the monopole current, wedge f. And so it's not 0, it's just broken. And so this is very different from the non-abelian case we saw before. In particular, this suggests that gauging the Chern-Weil current would be inconsistent with monopoles, since we would be gauging and breaking the same symmetry. Of course, there's something funny about this argument, because we have lots of string examples with U1 gauge fields that have monopoles and axions. So what's going on? There's some contradiction here. In order to resolve this, we can look at an example, which is the 't Hooft-Polyakov monopole. And it's what happens if we realize our U1 gauge theory by Higgsing an SU2 gauge theory by an adjoint scalar. In this case, we naturally have monopoles in the IR, which are finite, non-singular configurations of the gauge field. And we also have a conserved Chern-Weil symmetry in the UV, which is instanton number for the SU2 gauge field. Now in the IR, the 't Hooft-Polyakov monopole does break the U1 Chern-Weil symmetry as before. What I said before is perfectly valid. But there's a new feature, which is that on the 't Hooft-Polyakov monopole, there's a compact scalar sigma, which arises as a collective coordinate of the monopole solution. And if we're careful, when we Higgs the SU2 gauge theory down to U1, we find that this UV Chern-Weil current descends to this following combination of the Chern-Weil current for the U1 gauge field, as well as a current involving monopole degrees of freedom on the monopole world volume. And so this combination is conserved. And in this case, it's similar to what we saw before. There's a combination that's broken, but then there's still this combination that's conserved. More generally, we can argue that in a case where the U1 Chern-Weil current is gauged, that's equivalent to saying that the monopole has a world volume scalar sigma. We don't have to assume that this came from an SU2 gauge theory. This is just by general principles. This is well known. In d=4, this is the Witten effect, and it tells us there should be dionic bound states of the monopole and electrons, so electric charge. And in particular, these states should undergo monodromy as our theta angle, or our axion, goes from 0 to 2 pi. This makes sense because if our axion is dynamical, then in a region we can just dynamically change theta, our axion from 0 to 2 pi, and the spectrum has to go into itself under that transformation. It has to be consistent, so we should have a Witten effect. More generally, in higher dimensions, the monopoles are higher dimensional branes, and this says that we can dissolve electric charge in the monopole brane. And I should say we should expect this story when, in any case, where U1 can enhance to a non-abelian group. So any U1 that has the potential somewhere in moduli space to enhance should have this story. One upshot of this is that the consistent gauging and breaking of abelian Chern-Weil symmetries tells us a lot of details about the solubility of various branes in other branes. And of course, this is most powerful in theories with a lot of abelian gauge fields, like type 2 supergravity. So type 2 supergravity has all the Ramon gauge fields. These are various higher form abelian gauge fields. And what we find is that requiring the condition of no global Chern-Weil symmetries ends up reproducing a lot of features of d-brane interactions that we're familiar with in type 2 string theory. I don't know that we can reproduce every feature of d-brane interactions, but we get a lot of cascades of which branes can end on branes. And I think it's pretty nice that we can argue for this from the condition of no global symmetries. So let me conclude. So the basic point is just that these are symmetries that exist in gauge theories, and they have to be broken or gauged in quantum gravity. In the case of non-abelian gauge fields, this tells us about the necessity of an axion coupling to the instanton number, as well as certain of its properties as constrained by symmetry. For abelian gauge fields, this tells us a lot of details about the solubility of various branes in other branes. And I want to point out that this provides further evidence that these stringy features, these things that we're very familiar with in string theory, are just generic properties of quantum gravity. They're not things that happen only because we're looking under the lamppost. These are things that are required by the condition of no global symmetries. And so that's what I had to say. So thank you so much for listening. And I guess Tom and I are happy to take any questions.